Hi folks, welcome to Thursday's recitation video. I'm thinking some people probably join as we go along, but I'm going to get started doing some of the problems here. I'll share the link to the PDF of the problems in the group chat. This is on sections 15.3 to 15.4, really having to do with change of variables between different coordinate systems. Bear with me, my document cam's been a little bit finicky. I'm hoping it'll stay with us through the whole time, but it's been a little bit tricky in the past. So what I want to do is start by just talking a little bit about these different coordinate systems in general before we jump into the problems, and make sure we're on the same page about their meanings and how to convert between the different systems. So we've been working pretty extensively in Cartesian rectangular coordinates with x, y, and z. We need to be able to move between that and a two-dimensional system involving polar coordinates. We can understand polar in 2D, then cylindrical is very easy, and spherical is just a little bit different. So our first conversion factors in R2 between x and y and r and theta in a polar system, pretty straightforward here. It all comes from trigonometry, and in fact, really this whole section just comes down to doing good geometry to switch between these systems. The calculus ends up being fairly straightforward. So if we have some point in R2 whose coordinates are x and y, and so there's y and there's x. And we also think of that as being some distance r from the origin with angle theta to the positive x-axis. Just by right triangle trigonometry, we get the following conversion factors. So we have cosine of theta, that's adjacent over hypotenuse, that would be x over r. And sine of theta would be y over r. If we just take these and multiply both sides by r, we get conversion factors for x and y. So whatever our x variable was represented in polar coordinates would be r cosine theta, and y would be r sine theta. So one thing I should address is, why bother with these different coordinate systems? Last week we did a problem involving an ellipse, and we were able to leverage some of the symmetry, the rotational symmetry or the radial symmetry of a circle to look at an ellipse. An ellipse's equation in Cartesian coordinates is pretty complex. Like x minus h and y minus k divided by these a and b squareds equals 1 added together. It's like not the nicest equation. But there's certain geometric forms that are really easy to represent in polar coordinates, ellipses being one of them, and things that tend to have some sort of circular or cyclic nature to them. They just have easy representations. And we'll find a variety of surfaces in 3 dimensions that also have nicer representations or easier to work with in one coordinate system or another. The problems we've been giving you so far are very explicit in that you're given one coordinate system, typically rectangular, then asked to do the problem in a certain system. Hopefully what you'll develop by doing some of these problems is a sense of what coordinate system might be convenient to a problem if you're not specified which one to use. So here's some conversion factors for rectangular to polar. We could derive some ways of going from polar back to rectangular if we wanted to. Also that angle theta, you can see it would be like an arctangent of y over x. Those formulas aren't quite as important. We're typically just going between the coordinates using these ones. Okay, so in a cylindrical system, we have the same representation for x and y. And if we imagine a z-axis, I'll draw it coming out of the board like that. So there's our z-axis. You can imagine it pointing like up towards the camera. We get x, y, z. So all we're going to do then is just add a z-coordinate to represent coming up some height. So if this is a point right here, if that's point 1, that's in the xy plane, right? Z equals 0. And then we go straight up some amount. We're at a new point in 3-dimensional space, and we've entered a cylindrical system at that point. So the conversion factor between Cartesian and cylindrical coordinates, we use the same 2 for x and y, and then we're just adding a z coordinate anyway, and so z is just whatever the z value is. There's no conversion needed. One important thing when we're working with polar coordinates is to think about what happens to that area differential. So the area differential in Cartesian coordinates is just dx dy, right, in R2, and dx dy dz in R3. The geometry that we've introduced here the area differential, oh, there goes my webcam. The area differential is going to be r dr d theta. And that's also going to translate then back into our cylindrical coordinates as well. Let's see if I can get this thing to come back to life. I'm going to pause the video for a moment so I can bring back our dot cam. Okay, my dot cam is back to life. We'll keep going. If we have to record this in little bits, so it goes. All right, so cylindrical coordinates, again, like I've just drawn, the whiteboard is the xy plane, z is coming straight out towards the camera. So we have r, theta, and z as our three variables. And then the area differential in cylindrical coordinates, dA is r dr d theta. And then if we go into, sorry, that would be, I guess, polar there. And dV in cylindrical coordinates, we're adding that differential dz coming out of the whiteboard here. And so our volume differential is r dr d theta dz. So we want to make sure that we introduce that when we change variables here. Okay, so spherical coordinate system is a little bit different. We are going to use some of the same ideas here. So we'll still have that variable theta representing rotation in the xy plane. I'm going to draw the perspective a little bit different for this one. So just bear with me here. So here we have x and y and z in Cartesian coordinates. Okay, so again, like we did up here, if we imagine an angle just in the xy plane, right, indicating a direction formed from the positive x-axis. I'm going to put it here in the first quadrant just for illustration's sake. Okay, so again, that angle there is still theta. That's the same as in cylindrical or polar coordinates. We're going to add two more parameters here. We're going to use rho. So if we have some point like, let's say, up here, so elevated above that angle theta, the distance from the origin to that point is rho. Make sure I get my rhos. Okay, so there's rho. I'm really bad at Greek lowercase letters, apologies. So that's that distance from the origin to the point. Theta is the angle formed between the projection down onto the xy plane, that vector there, and the positive x-axis. And then our last angle is phi. And phi is the angle formed between, again, that vector, right? That's rho, or the vector has length rho. That angle phi is right here. It's formed between the positive z-axis and the vector going to our point here. And that's a little bit of a tricky geometry. I actually messed up a problem earlier in the week by using the complement down here instead of this angle here. It's not an angle of elevation up from the xy plane. It's an angle of declination. If you think back to geometry, there's some alternate interior angles here. So we could also think of phi as being the angle going from our point downward back to the origin there. That's our alternate interior angle there. So a similar system to spherical coordinates is what we use to locate points on Earth. If you think about if we were to give latitude, longitude, and altitude, those are in a way standing in place of a spherical coordinate system. Longitude would be given by theta. Latitude is not exactly phi. Up at the North Pole, we'd call that 90 degrees of latitude. So it is really more of an angle of inclination here, the complement to phi. And then rho, that distance, we could think of as being altitude. So we could locate a plane on Earth using latitude, longitude, and altitude, and that's very close to being a spherical coordinate system here. Okay, so some conversion factors here. So let's see, what would we do here? So to think about, I'm not going to do the full derivation of where these conversion factors come from, but they are important to know. I noticed that the key has them written right at the top of the page, but like the student version doesn't have them. I'll just flash them briefly up here, right? So hopefully you have these in your notes somewhere or in your book. I'm going to write them down on the whiteboard, not the full integrals, but just like what happened to x, what happened to y, what happened to z. Without doing the full derivation, to get z is probably the easiest one here, right? So z is going to be, if we think about this right triangle here, well, we have phi that's also up there, right, by alternate interior angles. We have a right angle that's formed there. So the right triangle trig that we have then is if we were to take cosine of phi, that'd be adjacent over hypotenuse, that would be z over rho. So cosine phi equals z over rho, and then multiplying both sides by rho, we get that z equals rho cosine phi. Okay, so to get x and y, what we'll do is we'll think about that projection into the xy plane, right? So we can use these previous conversion factors here for x and y, and then and instead of r though, we're thinking about like that distance out there, right? So how could we represent that distance out there? Well, again, using a trig function with phi, we can find that distance r. Well, it's not part of the spherical coordinate system. We can find that in terms of rho and theta. So I'll give you those right now. We don't need to go through the trig in two different planes there, but let's see. So we have x equals rho sine phi cosine theta. So rho sine phi cosine theta. And y is rho sine phi, sine theta. Okay, so here are our spherical conversion factors. And then the last piece here, if we're trying to look at a little change in volume here, our dV will be rho squared sine phi d type on here. So d rho d theta d phi. Okay, so we'll bring this back as needed. The important pieces are the conversion factors and then what happens to our volume differential as we switch bases. Okay, so let's take a look at the assignment here. Let's see, I'm trying to do this without erasing the work. Okay, so problem one, we're given the region above the sphere x squared plus y squared plus z squared equals 6, and below the paraboloid z equals 4 minus x squared minus y squared. So part A, we just want to sketch our region R. So let's see, I'll create a three-dimensional coordinate system. All right, so we got x, y, z. So our sphere would have center at the origin and radius root 6. Root 6 is between 2 and 3, so I'll just kind of estimate it's a little bit probably closer to 2 than 3. Perspective drawing, definitely not my forte, but we'll see what I can do here. Okay, so we got this sphere, not to scale. All right. And then above it, we have this downward opening paraboloid here. We can figure out what its intersection with the z-axis is by letting x and y equal 0. Z would be 4. So 1, 2, 3, 4. So up here, there's a little bit more room. We have this sort of downward opening paraboloid. Then again, by looking at level curves, we can see that the level curves in the z direction would be circles. So first thing for me to do, now that I've butchered that drawing, is to just like play around with the geometry here, figure out what we're going to need. One thing we need to consider is what our endpoints of integration would be. That would be, or that would at least involve the intersection with that paraboloid in that sphere. So let me just take a look and see if I can figure out when that would happen. So here we have x squared plus y squared plus z squared equals 6. And here we have z equals 4 minus x squared minus y squared. I'm just going to rewrite that in a slightly different format. So z equals 4 minus x squared plus y squared, or equivalently 4 minus z equals x squared plus y squared. And then what I can do is I can substitute in my first equation here. So if x squared plus y squared is 4 minus z, then the intersection would be 4 minus z plus z squared equals 6. All right, so if I subtract 6 from both sides, I get the quadratic z squared minus z minus 2 equals 0, and that factors to z minus 2 and z plus 1. Okay, so that tells us that the paraboloid actually intersects the sphere at 2 different values of z up here, and then it's going to cut through the sphere and intersect for a negative z value, z equals -1. We're really only interested in this upper intersection here. So z equals 2, right? That's that upper boundary for, I guess the lower boundary of our region, the top of the sphere there. All right, so let's see, what else do we have then? So if z equals 2, then the circle that we're looking at is x squared plus y squared plus 2 squared equals 6. Subtract 4 from both sides, we have x squared plus y squared equals 2. Okay, so we have a circle here, and its radius would be √2. Up here, it's our point 4. And that's a good basis for beginning our problem here. Let me grab my notes, we'll keep going. Okay, so maybe one more thing here. We're going to be using polar coordinates for the problem here. So we have all these x's and y's. One more convenient conversion factor, and I'll put this back on the whiteboard in a minute. If we think about a point in the xy plane that's distance r, well, by the Pythagorean theorem, that would be a right triangle formed with x and y as the sides of the triangle and r as the hypotenuse. So we do have one more conversion factor that's really helpful in this one, and that's just that x squared plus y squared equals r squared. So in converting this into polar coordinates here, double integral in polar coordinates, we're going to not have too much trouble converting these equations, right? So this one would just be r squared plus z squared equals 6, right? That's our sphere rewritten in polar. And then the paraboloid would be z equals 4 minus r squared. Right, there's our paraboloid. I'm going to do one more thing here. We are just dealing with positive values of z, so we don't have to worry about the plus or minus, but we could also rewrite this as z equals the square root of 6 minus r squared. Okay, so now we have two representations of z that are just using r, right? So we're going to be able to change this into just a two-dimensional problem here with r and theta because of those conversions there. All right, so we're asked to set up a double integral in polar coordinates to find the volume of r. So let's think about our boundaries. So we're bounded above by the surface that's our paraboloid, so 4 minus r squared, and below by 6, the square root of 6 minus r squared, right? So that would be that distance between these two here. So let's write that first. So 4 minus r squared minus the square root of 6 minus r squared, right? And then since we're integrating in polar coordinates, our conversion factor is going to be r dr d theta. Okay, so the other important part here is to make sure that we have our endpoints of integration correct. So first, let's think about our minimum and maximum value for r. Well, we figured out that the radius of this circle here is going to be √2, right? Because that circle is x squared plus y squared equals 2. So that's the largest that r could be. The smallest that r could be is 0 up here. So our endpoints of integration for r will be from 0 to √2. And our endpoints of integration for theta almost always will be 0 to 2 pi, right? That's a full revolution in the xy plane. It's a really rare problem where that's not the case. Okay, so here's our double integral setup. Hopefully all the pieces make sense. Here's our area differential, right? The idea is we're going to stack up these areas to create a volume. The difference between our two functions, right, that's the space in between our two surfaces written in polar coordinates. Here are endpoints for r, here are endpoints for theta. So when we have these multiple integrals, oftentimes this d theta, right, the theta differential, right, we don't have any thetas that show up in the equation here. If we have that radial symmetry, then it should be independent of theta and for a lot of functions. So that integral in terms of theta is just going to be 2 pi minus 0. We can actually evaluate that first. We can at least put it on the outside just to show like one step of how that comes about. Really what I'm saying is we can do this. We can go from 0 to 2 pi of just 1 d theta, right? And then within that, we'll have the following integral. I'm going to use some distribution here. By the way, this conversion factor, RD theta, is actually really convenient for this problem because the square root of 6 minus r squared, that's not an easy antiderivative. But if we multiply by r, it actually becomes easier. Now we have like a u substitution integral where we have u and we have u prime really easily found. So let me distribute that r across these terms here. So we have 4r minus r cubed minus r times the square root of 6 minus r squared. And all that's times dr. Okay, and endpoints are still 0 to root 2. Okay, so I'll do two things in this next step. I'm going to evaluate this theta integral. So that'll just be 2 pi out in front. And then we're going to evaluate the endpoints of the antiderivative here. So let's see. We'll go term by term. Antiderivative of 4r is 2r squared. R cubed will be 1/4 r to the 4th. And then if I have my u substitution correct, that's the 1/2 power. By the chain rule, we're going to be multiplying by negative 2r out in front. So I think our correct coefficient here would be 1/3, and we'll just check to make sure that that's correct here. So that'd be 6 minus r squared to the 3/2. Okay, so let's just check that, make sure I got that right. So if we think about differentiating, the 3/2 comes out in front. 3/2 times 1/3 is 1/2. Our negative 2r comes out in front, so we'd have a negative r times the square root of 6 minus r squared. So that looks good. Just be careful with the sign there for things like that. All right, I want to evaluate that at 0 and square root of 2. Okay, so we have 2 pi times the following. So if we plug in root 2, that would be 2 times 2 minus 1/4. Root 2 to the 4th would be 4. And then add 1/3, 6 minus r squared, so that would be 4 to the 3/2. Let's see, 4 to the 3/2, that's the square root of 4 cubed, so we can just think of that as the number 8. And then subtract these same things plugged into 0, so 0, 0. And then this last part here, that would be 1/3, 6 to the 3/2. Okay, so 1/3 times 6 to the 3/2. So 6 to the 3/2, that's root 6 cubed. So I can write that as 6 root 6, or again, simplified, that would just be 2 root 6. Okay. All right, so let's see. We have 4 minus 1 is 3. So 2 pi times 3 plus 8/3 minus, let's see, is that right? Yeah, minus 2 root 6. And then finally, I'll write all this in terms of thirds. So we have 2 pi times 9/3 plus 8/3 minus 6 root 6 over 3. So 2 pi times 17 minus 6 root 6 over 3. Okay, so there's my final answer. Sorry, I went off the page there. I believe there's a small typo just in the last step of the key that will be posted online. It's just the coefficient of root 6 here. I believe it's, in the key it's written as 2 instead of 6, but this should be the right answer here. Okay, so we'll pause for a moment and we'll look at this problem a second time using a different system. Okay, so part C here, we're going to revisit the problem as a triple integral in cylindrical coordinates. That should be very similar to what we just did in polar coordinates, given the similarity in coordinate systems there. So one thing I'm going to do here, I'm just going to write out like the general form of this triple integral without specificity to this function. So we're going to go from theta 1 to theta 2, and we're going to go from R1 to R2, and we're going to go from Z1 to Z2, and so we have some function of R, theta, and Z, and then our volume differential R dr. Actually, I guess I'll match should match in order here. So R dz, dr, d theta. All right, so here's our general form for this particular problem. We already have our function, I think, in terms of R, theta, and z. So you'll see a lot of problems like this where we ask you to do a problem more than one way and show that the answers are equivalent. This one's actually only a few steps here. So let's see. So if we think about our endpoints here, our endpoints of integration for theta are exactly the same. So 0 to 2 pi. Our endpoints of integration for r are also the same. So 0 to root 2. And now thinking about our boundaries for z, well, if we write those in terms of r and perhaps theta, this problem is really quick, right? Our lower boundary was that sphere, square root of 6 minus r squared. And our upper boundary was the top of that paraboloid, so 4 minus r squared. Right, so those are boundaries for z. Our function then is just, well, really what we'll get then is just r d z dr d theta, right? Because these are boundaries for z. So if we start integrating this, if we just integrate in terms of z, what we get then is we get z r dr d theta, right? Evaluated at the endpoints of 4 minus r squared and root 6 minus r squared. And then we've still left to integrate 0 to root 2 and 0 to 2 pi in the direction of theta. All right, so now if we plug in these endpoints and subtract, here's what we get. We get the integral from 0 to 2 pi and 0 to root 2 of the following difference. Well, 4 minus r squared minus square root of 6 minus r squared, and then times r dr d theta. And at this point, we've created an integral that's absolutely identical to the integral that we created in polar coordinates. So from this step out, like all our steps are going to be exactly the same. This is a good place to stop this problem, right? Our steps will be identical. We've convinced ourselves that those two approaches are going to yield the same answer. Okay, so same problem using a triple integral rapidly becomes the problem just in polar coordinates. Okay, so problem 2, spherical coordinates. So let's see what we have here. Use spherical coordinates to calculate the integral of f of x comma y comma z is the square root of x squared plus y squared plus z squared over the region x squared plus y squared plus z squared is less than or equal to 2z. So let's just take a look at some of the geometry here before we get too far into the problem. So if we think about level curves for our function here, if we set this equal to some constant squared both sides, we get the equation of a sphere centered at the origin. Since it's the square root, we'd only take the positive value, so maybe really a hemisphere here. I guess it doesn't really matter. We could have positive or negative values for x, y, and z. So yeah, we have spheres as level curves. And then this region, this inequality might be a little bit tricky to look at first, but I'll show you a trick for figuring out what's going on here. We have x squared plus y squared plus z squared is less than or equal to 2z. Well, if we want to think about this in just Cartesian coordinates, we could complete the square. So this is x squared plus y squared plus z squared minus 2z plus 1 is less than or equal to 1. So all I did there is I subtracted the 2z, actually write z, not x, from both sides, and then I added 1 to complete the square for z. So if you're curious about what this looks like, this is the interior of a sphere, so x squared plus y squared plus the quantity z minus 1 squared is less than or equal to 1. So that's a unit sphere centered at 0, 0, 1. And since it's an inequality, it would be on the interior of that sphere. Okay, so let's start converting some of the stuff into our spherical coordinates. So again, maybe I'll bring back that whiteboard here just momentarily. So spherical coordinates, we have z as rho cosine phi, x as rho sine phi cosine theta, and y equals rho sine phi sine theta. And then importantly, if we just want rho, right, rho squared would be x squared plus y squared plus z squared, right? That's the distance squared. It just comes from our distance formula in 3 dimensions here. Okay, so let's start to set this up here. So we're going to have a triple integral. And I'm going to write it in its general form first. So we're going to go from rho 1 to rho 2. And we're going to go from phi 1 to phi 2. We're going to go from theta 1 to theta 2. And then our conversion factor is rho squared sine phi d rho d phi d theta. Right, that's the general form for our change of coordinate system triple integral here. All right, so now what we need to do is figure out what that means for this particular problem. All right, well, let's take a look at rho first of all. So rho is going to vary. Rho is the distance from the origin. So rho's minimum value would be 0, right? And its maximum value can be given just by looking at a little bit of geometry here. Right? What we want to do is potentially write this in terms of phi here. What I'm going to do is take this inequality here. We just looked at this in Cartesian coordinates. If we translate this back into spherical coordinates, it behaves pretty nicely. So x squared plus y squared plus z squared, that's just rho squared, right? So rho squared has to be less than or equal to 2z, okay? Well, one thing that we know about z, we can convert z into spherical coordinates just using one of our formulas there. I'll rewrite it here instead of bringing back the whiteboard. Z is just rho cosine phi. And so if we substitute that into our inequality, we get that rho squared has to be less than or equal to 2 rho cosine phi. Okay, divide both sides by rho, and here's our boundary for rho. Rho has to be less than or equal to 2 cosine phi. Okay, so that then gives us a boundary on our integration here. So our lower bound for rho is 0. Our upper bound is 2 cosine phi. So let's see. Bear with me for just a sec here. Okay, so I forgot one small thing here. Here's our function defined in rectangular coordinates. If we rewrite it in its spherical coordinates, so as a product of r phi, and theta. Well, x squared plus y squared plus z squared is rho squared. And the square root of rho squared is just rho. And so what I forgot to put in here is that we need our function f, right? We need something to integrate times this conversion factor. So our function written in terms of spherical coordinates is just rho. So we have a triple integral. I'll come back to the endpoints for phi and theta in a moment. Our function, I'm just writing it as f. It is f of rho phi theta. But what we just figured out is the one we're dealing with is just rho. So there's our function, right? And then we're going to multiply that by rho squared sine phi d rho d phi d theta. I just want to label this so it's really clear where these things came from. That's our volume differential in spherical coordinates, and this is our function f. All right, so that's where those two things came from. Let's consider the endpoints for phi and for theta. Theta is often going to be the easiest, like I mentioned before. We're going to go 0 to 2 pi in almost all cases. Now, phi is that angle of declination, and it actually puts maximum and minimum value on it. So if the angle of declination, or the angle formed between the x-axis, sorry, the z-axis and our point, obviously it can be at the minimum it could be would be 0 here. And the most it could be, if we were at a point actually like on the xy plane, right, that a point on the xy plane would have phi equal to pi over 2, a 90-degree angle there. So we'll often see this, not in all cases. In fact, in the next problem, our boundaries on phi will be a little bit different. But again, if we sort of reverse the problem and think about an angle of elevation, like looking up from the surface of the Earth, the most that we could have as an angle of elevation would be 90 degrees. Likewise, we're going to see that the boundary for that angle of declination from our point back down will be maximum of pi over 2 in most of the cases that we see here. Okay, so I've set up my triple integral. I got my dv, I got my function, I have my endpoints. These are my endpoints for rho, right? That came from our inequality. Endpoints for phi came from just the geometry of the problem. Likewise for theta here. Okay, so again, I will do the convenient integrals first, so I don't see any thetas, so we can evaluate that independently at first. The theta integral will just result in a coefficient of 2 pi. I'm going to wait to integrate phi. Phi is going from 0 to pi over 2. And I'm going to take that antiderivative for rho right here. So we have rho cubed times sine phi. And so that would be then rho to the 4th power times 1/4. I'll just maybe put that out here. So 1/4 times 2 pi, rho to the 4th, sine phi d phi. And we need to evaluate that at the endpoints of 0 and 2 cosine phi. Okay, so when we do that, we'll take 2 cosine phi, raise it to the 4th power. So let's see, what do we have here? We have a pi over 2, integral from 0 to pi over 2. Rho to the 4th would be 2 to the 4th is 16, so 16 cosine to the 4th phi sine phi d phi. And again, our change of base, or sorry, our change of coordinate formula provides us with really like the exact key that we need to do a U substitution for our final calculation here. So let's see, what do we have? I can pull that 16 out. So 16 can come out here. So we have 8 pi. 16 times pi over 2, that's 8 pi. So my antiderivative, I have cosine to the 4th times sine phi. So I think that would be, let's see, negative 1/5. I always have to check these when I do them. So negative 1/5 cosine to the 5th phi. Again, evaluated at 0 and pi over 2. So let's just check that by differentiating. 5 comes down. We'd have negative cosine to the 4th the derivative of cosine is negative sine, and so we'd have a positive cosine to the fourth sine phi. Okay, good, that's what we want. Problem's almost done. So we have 8 pi, and then cosine evaluated at pi over 2 is 0, right? And cosine evaluated at 0 would be 1. So we have 0 minus negative 1/5, right? So 0 is when we plug in pi over 2. Negative 1/5 is when we let phi equal 0. And so then our final answer is just 8 pi times positive 1/5, so 8 pi over 5. Okay, so hopefully that makes sense. What I hope you're seeing in these problems is most of the work goes into just the geometry, figuring out how to translate our problem from rectangular coordinates into another coordinate system. Okay, I've zoomed in a little bit just so it's hopefully a little bit clearer and you're looking at what I'm writing here. Here's problem 3. Problem 3 is going to ask us to do a problem using both cylindrical and spherical coordinates. We now have a little bit of experience with both of those, and this is a good problem also to reflect on which is the easier way to do a problem like this. So here we have a region R bounded below by the plane z equals 1 and above by the sphere x squared plus y squared plus z squared equals 4. All right, here's the hardest part for me, that's sketching the graph. So this one shouldn't be too bad. It might be hard to draw, but not too bad to imagine. So here is our x and our y axis. The plane z equals 1, right? That would just be 1 unit above the xy plane and parallel to it. Our sphere is centered at the origin and has radius 2. Maybe I'll change our scale a little bit for a better picture. So I'll say that's 1, this is 2. So our sphere then, and the sphere is going to look something like this. And draw the xy perspective part first because it's harder for me. So there's our intersection with the xy plane, and then our intersection with the plane there. And so there's our sphere, not super symmetrical, but good enough. And then our plane cutting through it, right, it's going to sort of slice, right, it's going to slice the top of our sphere, right? So we're talking about this like upper section here, the slice of the sphere. Okay. So hopefully that makes sense what we're looking at up here. Okay, so let's figure out some things about this. We know we're going to use cylindrical and spherical coordinates. So let's consider first this boundary here. All right, so that's the intersection of the plane z equals 1 and the sphere x squared plus y squared plus z squared equals 4. So if we let z equal 1, then we have the equation x squared plus y squared plus 1 equals 4, or equivalently x squared plus y squared equals 3. All right, so obviously that's a circle of radius √3. In cylindrical coordinates, x squared plus y squared is just r squared, right? So this is the same as r squared equals 3, or equivalently r equals the square root of 3. So that might be useful in cylindrical coordinates. If we consider a point on that circle, I'm going to just draw this triangle, right? So a triangle coming up to that point there on the side. So let's do a little bit of geometry there. So if that's our point, x comma y comma z, we know that the distance to that point is rho, right? So again, let's imagine what that's going to be then. We know that the height is 1, right? That's z equals 1. We know that this distance from the origin out to its projection downward onto the xy plane, that's r, right? That's r there. And in this case, it's also √3. So by the Pythagorean theorem here, I think what we can see for rho is that rho would equal 2 there, right? That's a very specific triangle. We have 1, √3, and 2. That's a 30, 60, 90 triangle, where this angle right here, that would be pi over 6, and then their angle right in there would be pi over 3. Well, that angle right there, right, that's the same as phi, right? Phi appears both here and here. So at this boundary point here, in spherical coordinates, we would have, I guess, is that our upper or our lower bound? That's the interesting thing to think here. So if we were up here, what would phi be? Well, the angle formed would be 0. So we're in between 0 and pi over 3 for our integral here. Hopefully that part makes sense there as well. Okay, so let's see, we have some boundaries. So phi will be in between 0 and pi over 3. That'll be helpful for endpoint of integration. And let's see, what else do we do here? So our sphere x squared plus y squared plus z squared equals 4 in cylindrical coordinates. That's r squared plus z squared equals 4, or equivalently z equals the square root of 4 minus r squared. And that might be helpful in changing our integral here. In cylindrical coordinates, that sets some boundaries, right? Our lower boundary would be 1, upper boundary would be the sphere here. Let's see what else we can do. In terms of theta, hopefully it's clear from the geometry of the problem that theta will vary from 0 to 2 pi. So we got theta, we got phi. Let's think about rho here for a minute. Well, the sphere, right, the sphere itself has radius 2, so that puts some restrictions on what we'd see here. And rho, the smallest value really could be a 0, but we're just looking for that upper region there. So I think what we're looking at here is a minimum value of rho that would be 2. Let's go get my notes here, see the best way to represent this. Okay, I want to do one more thing here. So if we consider this point here, I just want to do one more thing for phi here that will be helpful for our endpoints of integration in part C. So if z equals 1, and I'm just going to sort of redraw this triangle here. So at the lower endpoint of integration, here we have z equals 1. Here we have phi. Right, and so phi is actually also up here. And then here's rho. One relationship that we can see here is that cosine of phi, that's adjacent over hypotenuse, so 1 over rho. And if we solve this for rho, we get rho equals 1 over cosine phi, or if you prefer, secant phi. So that'll be helpful when we look at spherical coordinates. I'll come back to that in a moment. That's a nice result of having the plane z equals 1 being our lower endpoint here. Okay, so let's go cylindrical coordinates first. So we're going to be setting up a triple integral first in terms of z. So our endpoints for z in this problem, the smallest z could be is 1, right? That's at the boundary of the plane where the plane intersects the sphere. And the most that z could be would be our upper surface here. So lower endpoint for z is 1. Upper endpoint for z, I think we just found that right here in terms of r is square root of 4 minus r squared. Okay, so there's our boundaries on z. And then moving outward, we want to talk about boundaries for r. So let's see, r. I think what we decided here, based on our geometry, if we think of that projection down, the largest that r could be is root 3. And the smallest r could be at the very top of the sphere would be 0. So our boundaries for r are from 0 to root 3. And finally, for theta, unsurprisingly, 0 to 2 pi. All right, so what we need then is we need to consider our volume differential. So we have r dz dr, d theta. And take a second, check, make sure that's right. So one thing hopefully you're noticing is when we do these triple integrals, we have to integrate more times, but what we're integrating is pretty straightforward here. Right, we didn't really need to do any conversion within the function. We're all doing that via the boundaries of integration here. So there may be problems where that's convenient to do. Okay, let's start integrating. So again, the theta integral, not very interesting. I'll just give us a 2 pi on the outside. I'm going to wait to evaluate my integral for r. And then let's take a look at what's happening to z. Okay, well, so z, we just had we have an r dz dr d theta, so we still have an r times z times d theta. And then the endpoints for z are going to be square root of 4 minus r squared and 1. And so we have 2 pi. Plugging this in, let's see what do we have here. So I'm gonna combine two steps here. We're gonna get the difference of square root of 4 minus r squared minus 1, right? That's what's gonna happen when we plug in our endpoints. We multiply by r, and that's gonna be key in the next step. So hopefully it makes sense what I'm doing here. Okay, so plugging in z, we'd have the square root of 4 minus r squared is the upper endpoint. That's gonna be multiplied by r though, so I'm gonna do that step right there. And we're subtracting 1 multiplied by r. And that's all still times d theta. Okay, so hopefully that makes sense there. Okay, now time to integrate with respect to r. Again, the conversion factor gave us just what we needed for this integral here. Otherwise, it'd be a trickier antiderivative. We have most of what we need for the antiderivative there. So let's see, we have 2 pi times, well, we're going to get a 4 minus r squared to the power of 3 halves. And I think what we need here is a negative 1/3 as our coefficient. Let me just check, make sure that that's right. So 3 halves comes down, multiplies by negative 1/3, so we get negative 1/2 times negative 2r gives us positive r, so that looks good there. Minus r squared over 2. And those are being evaluated at the endpoints of root 3 and 0. And so let's see what we get then, like 2 pi. So if we plug in root 3, we get 4 minus 3 is 1. Any power of 1 is just 1. So we should have a negative 1/3. Plugging in root 3, we get just minus 3 halves, so negative 1/3 minus 3 halves. And then we'll subtract the lower endpoint plugged in. So plug in 0. 4 to the 3 halves is 8. So we have a minus negative 8/3, if I got that right. That minus negative 8/3. And then that part will just be 0. Okay, so let's see what we end up with here. Converting these to sixths. We have 2 pi and negative 2/6 minus 9/6 plus 16/6. So let's see, that's 16 minus 11 is 5. So 2 pi times 5/6, or equivalently 5 pi over 3. So not bad, right? There's only one integral that was at all tricky, just a little u substitution there. Let's see how this goes with spherical coordinates. So again, let me write our volume differential first. So just rho squared sine phi d rho d phi d theta. And let's talk about endpoints of integration one at a time. So rho, what did we decide about rho? Let's go back to the top of the page here. So we had some restrictions on phi. On phi up here, so those will come in a moment. rho at our intersection of the plane and the sphere, rho equaled secant theta. All right, so that was our lower, sorry, secant phi. That's our lower endpoint of integration. That's the lowest value for rho. And the greatest value for rho would be straight up to this point. That would just be 2, right? That's the radius of the sphere. So we'll go from rho equals secant phi, right? That's at our intersection here, to rho equals 2, at the upper point here. And let's see, next we'll look at phi. So we did rewrite our inequality here. Phi should vary between 0 and pi over 3. So 0 to pi over 3. And theta, unsurprisingly, 0 to 2 pi. Okay, so here's our triple integral. I'm going to do the same sort of trick I did before. We'll just deal with theta first, so 2 pi. I'm going to keep the integral for phi for a moment later, so 0 to pi over 3. And then I will integrate in terms of rho. So in terms of rho, rho has power 2, so we should have 1/3 rho cubed sine phi d phi. And we need to evaluate that at the endpoints of 2 and secant phi. So what does that give us? That gives us, we'll combine that 1/3 and that 2 pi. So we have 2 pi over 3 times the integral from 0 to pi over 3. Okay, if we plug in 2, let's see, that would give us, I think, 8 sine phi. I've already factored out that 1/3, so 8 sine phi minus our lower endpoint here. So we'll plug in secant for phi. I'm sorry, for rho. So that's 1. I'm going to write it in terms of cosine here. So 1 over cosine theta cubed phi. Boy, sorry guys. I'm sine phi. Okay, hopefully I got that right there. And again, right, we're worried about powers of cosine. Not so bad if we also have a sine there. Okay. And by the way, just to take a look more closely, this will be the trickier part to integrate. Remember, that's just cosine to the -3rd phi times sine phi. So we can probably just consider this using powers of cosine. It shouldn't be so bad. All right, so 2 pi over 3. Let's integrate now in terms, or actually, I guess we gotta still do our antiderivatives here. So 8 sine phi, that would be -8 cosine phi, right? And here, let's see, what do we need to do to integrate? We need to increase that power by 1. So cosine to the -2nd phi. All right, we'll need to introduce a coefficient here, so we'll need that 1/2 out in front. And let's make sure that that gives us what we want then. So let's see, do we want that minus or plus? Okay, so if we take the derivative, we get a negative sign, then we get a -2, we have a -1/2. 3 negatives multiplied together gives us the negative sign that we want here. Okay, and then so we're going to evaluate this at endpoints of 0 and pi over 3. Okay, so cosine of pi over 3 is 1/2. That's convenient. I'm going to just move us over here. So we have 2 pi over 3 times the following. So -8 times 1/2, that's -4. And then minus 1/2 cosine to the -2nd phi. Okay, so that would be 1/2 to the -2nd power. So that's the reciprocal of squaring 1/2. And so that should be, I think, 4 times -1/2 is -2. And so that's just our upper endpoint of integration here. And then we're going to subtract what we get when we plug in phi equals 0. So cosine of 0 is 1, so we'd have negative 8 minus 1/2 times 1. Okay. And so 2 pi over 3. So negative 4 minus 2 is negative 6, minus negative 8 is positive 2, minus 1/2 is 3/2, I believe. Let me make sure I did that right. Negative 6, 2. Oh, sorry, this should be plus 1/2. So we have negative 6 plus 8 is 2, minus negative 1/2 is 2.5. So 5/2. There we go. And cancel the 2's, and we get 5 pi over 3. So same answer. All right, so a lot of details to attend to here. One of the things I hope to take away from these problems is really, it's all in the setup. It's just about getting our endpoints of integration correct and translating our functions in between these different coordinate systems. I'm happy that we have notes for some of these. Those conversion formulas are just in that kind of like have to memorize and know category. I'm going to pull those up just one more time before I finish the video here. We will post a key for this as well. And at the top here, here's our change of variables formulas. So polar, cylindrical, spherical. There's a very small typo here. We don't want a dz in our spherical coordinates. We want, I think, a d rho there. Okay, so thanks for folks who tuned in. Please keep posting online. Feel free to schedule some meetings with me. It's fun to see folks. Hope everyone's well, and I'll see you next week.